Um, so in the previous lecture, at the last minute, we have defined what a subgroup is. Let's just start by remembering this, right? So it's basically a subgroup of a group. G is a group in here, and we talk about this subgroup. So it's essentially a subset, but together with the operation that's defined on G, which is also defined on the subset as well. This subset is also satisfies the properties of a group. So that's it really. And then from here, we said that the identity must be inside the subgroup necessarily. And if H contains any element, then the inverse of that element should also be in the subgroup as well, and things like that, right? There are a few properties. So this is basically, we are going over this because this is the one of the essential terminology that we are going to use frequently. And then I have said that this is the mathematician's version of defining the subgroups. Well, it's not a definition, but it's a theorem basically. So to show that a subset is really a subgroup, then you only need this operation in here. So for any two elements, the inverse of one of them multiplied with the other, is it really in H? So by using this, you can show that the identity must be in H. For every element, the inverse should be in H, and so on. I just suggested that you had to, you just do it yourself. Okay, so the next thing is the direct product. Let me just say it like this. This is the direct product of groups. Again, this is purely mathematical, but this is I mean, this is one way of obtaining larger groups. And also this is a useful method for analyzing larger groups into smaller ones. And so as a result, let's go over this one. So in that case, I'm just going to go back to the old notation of showing the operation explicitly, all right? So let's say that I have two groups. I'm going to call them as G and K, for example. Why? I don't know. Let's say that K has an operation which is shown by O, and G is as an operation shown with star. So let's say that the identity in here is EG and EK. I don't know. So these are the identities. Okay, so I know that in mathematics, we have a way of defining the cross product of the product of, or the direct product of sets. So basically, these are elements of the form like, I mean, you just take an element from G, and you take an element from K, and then whatever this, these kind of elements form the elements of this direct product. Just remember this. I don't know. I mean, this is something that we actually use a lot, like let's say R cross R, which is basically R squared. These are basically elements of that form. In any case, I mean, this is something that you already know from set theory. That is why I'm doing this. In any case, what we do is we just define some kind of an operation on this product set. So let's say it like this, define an operation. I'm going to show it with a, let's say, a central dot in that case. So as a result, let's say it like this. If I take an element from this set, let's say this is G1, K1, the operation of this element with another element from the set, G2, K2, this is defined as, let me write def in here, as the two tuple formed from G1 operation with G2 and K1 operation with K2. All right. In that case, let's say it like this. You can show that this product set together with this newly defined operation is a group, well, called the product group, right? Let me say it like this. It's called the direct product of G and K. Why we call it as direct product? There's also a subtle concept called indirect product, which has nothing to do with us, right? Well, at least it is too complicated for us. So as a result, we don't define this, but this is important because this kind of simplifies the analysis of the structure of some of the groups. So you can easily see that, for example, this element is identity. This is quite easy to see. Yeah, whatever. If I have an element like GK, then the inverse of that element is basically the tuple formed from the inverses. And there's another thing in here. Yeah, I think I don't need to talk too much about this. So this is kind of obviously is a group. So as a result, I'm not going to say much, but there's one note in here. So just note. So I'm just going to define a particular subset in here. So let me call this as A, for example, is defined of elements of the form where the first in a tuple, the first element is an arbitrary element of the group G. The second element is an identity of K, right? So G in G. Let's say it like this. So basically, these are elements where you can think of it as like the group G is multiplied with the identity of the group K. Okay, so in that case, A is a subgroup of the product group. And moreover, it is isomorphic, isomorphic to the group G. So somehow, in this direct product, there is some kind of a copy of that, that group that was multiplied as a subgroup, right? And similarly, I'm going to do it like this. B is basically the elements of the form formed from the identity of the group G and an arbitrary element of the other group. Let's say it like that. So you can think of it as the product of the identity with the other group. Again, B is also a subgroup. Subgroup of G cross K, and moreover, B is isomorphic to K. I mean, these two groups are essentially the same. They had the same multiplication table. All right. So as a result, a direct product group somehow contains copies of these two groups as its subgroups, right? That's an important thing. There's another feature in here. There's another note in here. So let's say it like this. All elements of A commute with all elements of B. So I can show it like this. So just take an element from A, multiply it with an element from B. So that's the same thing as the product in the opposite order. So because we know that in both cases, I'm going to get this tuple in here. So this is basically some kind of an arbitrary element of the direct product group. I can actually express it as the product of one element in the subgroup B and one element in the subgroup A. And in that case, the order is irrelevant. I can just change their orders like that. All right, so there's also another thing. So that means every element of the direct product group can also be written as in terms of these. So as a result, if we are given some kind of a group, right? Let's say it like this. So that's the question in here. G, K, H, I, J, K, M, N, P. I usually use G for an arbitrary group, but let's say that, I don't know. Let's say that L is the name that we give. So let L be a group with a terrible name. Let L be a group, all right? Can we express L as a direct product of two smaller groups? So that's the question that I'll try to answer, but obvious that because of the analysis in here, you can see that there are some certain conditions for L being a direct product of smaller groups. Basically, it should have these two special subgroups. So let's say it like this. So the answer is yes. Right? Answer is yes if the following is satisfied. Following conditions are satisfied. Okay, so the first one is, no, it's not, it's the only one. Sorry, the following condition, but this thing has some conditions. So let's say it like this. There are two subgroups A and B of L. L has these two subgroups such that, so the first condition is all elements of A commute with all elements of B. So that means if I write down in math notation, is something like this, right? If A is an element of the subgroup A and B is an element of the subgroup B, in that case, this implies that AB product is the same thing as BA product. I just forget about this multiplication symbol for the group. I'm going to use the same one for all situations because this is basically what it is. So we are basically specifically talking about the group operation within a group given as L, right? L is the group, so the operation is defined on there. So the group operation inside A and inside B, they are the same. In any case, so there are these two subgroups. Their corresponding elements commute. The second one is this. A and B have the only common element of A and B is identity. We know that identity is an element of all subgroups, so as a result, the intersection of A and B cannot be empty. It has to be identity. We are saying that the intersection does not contain any other element than the identity. So as a result, these two subgroups have the minimum possible intersection. Okay. So that's kind of important for the third one. So every element, let's say, I don't know, G of L can be written as a product of elements of A and B in a unique way. Okay. So there are these two statements in here. The first one is it can be written. Let me write it down like that, right? I don't need to specify it like that. Sorry. I can erase this G in here. So every element of L can be written as a product of elements from A and B, and it can be written only in a unique way. So that means, so let's say it like this. If G is an element of the full group, then there are unique elements A in A, B in B, such that G is equal to AB. Okay, so the uniqueness is important. So you cannot have a different kind of a product producing the same element. You have only one way to express any given element of the L, right? That's basically implicit in the direct product. So you can essentially see that this property is, all of these three properties should be satisfied in a direct product. But you can, I'm going to ask you to show them by yourselves. So in that case, you can show that the group L is actually, let me say, isomorphic to the direct product of these two subgroups. So you can define the direct product of these two subgroups. So formally, this is a different group, but in any case, there's a one-to-one correspondence between the elements of the group and this one. This is actually an isomorphism. So the group operations in both sets are going to be the same. They are going to yield the same result.
Sir, can I ask something here?
Yeah.
Do A and AB necessarily have to have the same identity element?
No, there's just a unique identity. So, I mean, they cannot have any different identities.
Because, well, we were talking about direct products in the previous discussion. We had J and K. They didn't have necessarily the same identity. We defined.
Yeah, but in that case, we were explicitly talking about different sets. They were different there, right?
Okay.
You're talking about this, right? G is a group and K is a group. So G might be a matrix group and K might be, I don't know, the set of integers, for example. But where this is addition, for example, right? In that case, we're talking about different sets. So the ident element is the ident matrix in here, and the ident element is the zero number here. So in this case, they are different, but here, this is a different situation. We have a group L, so let me show it like this. Group L is a set, and we're talking about the subgroups of it. So A and B are two different subgroups of this set. So therefore, they have to contain the identity of the full group. So in that case, the group operation is the same throughout. And that's the reason why I didn't use an explicit group operation in here, because of that reason. Okay?
Okay, thank you.
So in any case, this is a little bit abstract, but let's just give an example. Right? C6, this is just a cyclic group, right? So you can show that this is basically is a product group. So it can be expressed as the direct product of the cyclic groups of orders 2 and 3. Reason is something like this. So, I mean, since the cyclic group is usually defined symbolically, I'm going to do this. So there's some kind of a generating element, let me call it as A. and then the elements are just the powers of this A up to A to the 5. Okay, and then let me use a different color here. I can choose, for example, I know that A cube is an element with order 2, so I can define, let me call this as like this. So I can define a subgroup from identity and A cube. So the identity should be there because all groups should have an identity, and it should be the same identity in here. What else? A cube multiplied with itself gives us identity, so therefore this is a subgroup. Okay, and then let me use a different color again, green this time. So I think I'm going to take A squared in here and A to the 4 in here. So B is basically identity A squared A to the 4. This is also a subgroup. So in any case, you can see that A is actually a cyclic group, and B is also a cyclic group with order 3 in that case. So A squared has order 3, A cube has order 2. So these two are cyclic groups. So in a way, this cyclic group contains subgroups which are also cyclic. Can it contain subgroups which are not cyclic? I don't know.
I guess all subgroups of a cyclic group must be also cyclic. I guess there is a lemma, or let me check.
Say it again.
I think there's all subgroups of cyclic groups must be also cyclic. I guess there is a theorem or a corollary related to that. Let me check. Okay.
All right. Yeah, I don't know. It is possible, but it's not important for us, right? So as a result, so what I was saying, yeah, so you can easily check that these two subgroups satisfy all the properties. So the commutativity is obvious because the whole group is also commutative, right? So therefore, no problem with the commutativity. A intersection B is only the identity, that's okay. And then you just take any element and try to express it in as a product of elements of A and B. You can easily see that the A cross B has 6 elements. Okay, and so as a result, it is kind of obvious that there are 6 elements. Let's see. So if I consider all the possible products between A and B, sorry about this, A multiplied with B also has 6 elements. But I'm just going to explicitly do this calculation. So identity A cube multiplied with identity A squared A to the 4 is, if I multiply with identity first, then I'm going to get these elements, sorry, A to the 4. And if I multiply with A cube, then I'm going to get A cube A to the 5. And so A cube multiplied with A to the 4 will give me A. Okay, so you can basically get the whole, all of the elements in the, within the group. And so therefore, this basically shows that, I mean, let me show it like this. So A cross B as a group then is isomorphic to C6. Any group of cyclic with saying, yeah, okay. Thank you very much. Hocam biraz yukarı kaydırabilir misiniz? I don't know what you're talking about, so I don't know when this comment is made. Whatever. So in any case, so then there are these I mean, there are these conditions, therefore. So if I want to consider a group, a given group as a product group, we can do this analysis. We can try to see if there are these two subgroups of that special form, and then, we do the analysis like that. So there are many examples of these. So this is just a technical example, so probably that's too complicated, but there are some, I don't know, the rotation groups with inversion, for example. I'm just going to write this thing down in here, but I'm just going to explain this later, right? So SO3 basically is the rotation group that contains only the rotations, and O3 is the group that contains also this mirrors and things like that. This is actually a product group. And you can easily see that this is a product group. So these kind of things makes the analysis of these groups easier, because you somehow analyze the group into group structure by analyzing the simpler groups, right? So since I didn't define what these things are, so let's just forget about this for the moment, all right? In any case, I will also say that in 2 dimensions, this doesn't hold, but when time comes, I'm going to discuss all of these. Okay, so product groups, and then, okay. All right, so this is also quite technical, and we are not going to use it in the course, but this is the part of thing that you should actually always keep in mind, right? So we start with this. So let's say that G is a group. I'm going to define the cosets basically, but let me not put a title in here. So H is a subgroup of G. So in any case, this is the definition. So let's say it like this. For any element G of the full group, we consider this product in here. So let's just remember the product of an element with a set. What we do is like, or the product of 2 sets, what we do is we just take the product of G with every element of H and put it this as a list. So in any case, this is called the left coset. This is a left coset of the subgroup H. And if I multiply the G from the right, this is called the right coset. Okay. So again, remember these, right? Just remember. If H is, if I don't know, the order, the elements like that, H1, H2, let's say Hm, one of them is identity, probably this one. In any case, G times H is defined as GH1, GH2. I basically take the product of each and every element with G. And HG is H1G, H2G, and so on. So the set itself is called a coset, basically. So it's not the product itself, but the set itself. It's called the coset of the subgroup. Let's see. So previously, we have just noted that because of this rearrangement lemma or the cancellation rule, all of these elements are different from each other. And so therefore, this coset has exactly the same number of elements as the subgroup, right? So that's something that we need to state in here. So all cosets, have the same number of elements. Basically, the number of elements in GH is equal to the number of elements of the subgroup. And that's also for the right coset. So all cosets, whether it is a left coset or a right coset, doesn't matter. They have the same number of elements. So this is something that we are going to use later at some point. So let me say it like this. H is a coset of itself. Let's start with this. One of the cosets of the subgroup is itself, basically. Itself is also a coset because identity multiplied with H is equal to H. And that's equal to H times E. So therefore, this is both a right coset and a left coset. So let me actually say it like this. H is both a right coset and a left coset. Okay. All right, so that's one of the first things. The second one is this. Let's say it like this. If H is an element of the subgroup, then because of the subgroup property, H multiplied with H is the subgroup itself because of the closedness property. And because of the rearrangement lemma, if you remember the rearrangement lemma, this is true for any group. So if you take a group and multiply all its elements by an element of the group, then you get all the elements of the group, but in a rearranged way, if you remember it. And in that case, basically, this is just a special case of this, but this is applied to a subgroup of some big group, right? So this kind of tells you that if, I mean, for forming the coset, if instead of an arbitrary element of the group, if I use the element of the subgroup, then I'm going to get the subgroup itself. All right. So again, H is a coset, a right or a left coset, but I don't have to use identity in here to obtain this coset, right? Any element of the subgroup is basically can be used. So this is the general idea in here. So different elements of different elements, let's say, can be used to produce the same coset. Whether it's a left coset or a right coset, doesn't matter. So I don't know, for the coset H itself, this is obvious. But I'm just going to do a few things. So this is in general true. Let GH be a left coset. Let K be any element in that left coset. In that set, right? So I'm going to claim that GH can also be generated by KH, right? This is actually a theorem, so let me just box this. So if I have a coset, doesn't matter what it is. So I have a set, and I know that this is a coset. I would like to generate it by multiplying an element with the group, and basically any element of that coset is going to do. This is kind of abstract, but in the examples we are going to actually see some nice examples of these. But I'm just going to show it like this. So the idea in here is this. So this is kind of the proof. So first, I know that K is in GH. So let's say it like this. H is equal to H1 to HM. I know that GH is this. GH1 to, I don't know, GHM. I know that K is somewhere in here. So there's some kind of an element in here. Let's say GHI, which is equal to K. All right. Okay. So therefore, K can actually be written as this G multiplied with some element of the subgroup. In any case, if that's the case, then K multiplied with H can be written as G multiplied with HI multiplied with the subgroup. But this is the associativity that I'm going to use in here. So I can then express it as in this form. So first I multiply the subgroup with this element and then this element. But I know that this is associativity. I know that this is equal to the subgroup, so that's the coset H. Well, then this coset is equal to G times H. So that's basically what we wanted to prove. So that's the end of the proof. All right. So basically, we generate a coset by its elements, right? Something like that. So this is going to be important, and so similarly for the right cosets, right? So let me write it as a comment in here, right? As a yellow comment. So this is similarly for the right cosets, right? So this is for a left coset, but for the right cosets as well, you can do the same thing. All right, so next, this is kind of trivial. G is an element of G times H. So if I produce a left coset by using element G, then the left coset itself should contain this element. All right. So that's kind of obvious because I know that, for example, let's say it like this. One of these elements is identity, whatever. So let's say that H1 is equal to identity. So in GH, therefore, the first element is GH1, but this is G times identity, so therefore this is equal to G. So therefore, G is an element of GH. All right, so this kind of completes these two things somehow complete to each other. So there are some certain subsets which we call as cosets. They are generated by just multiplying the subgroup with some certain elements. And which elements give a particular coset? Well, basically the elements of the coset give these, something like that. All right, there's this last theorem in here, which is the most important one. Two left cosets are either identical or disjoint. Disjoint means they don't intersect. They have empty intersection. So I'm going to show it in the mathematical language in here. So let's say it like this. Let's say it like this. Let G1, G2 be any two elements of G. I'm still considering this H as a H is a subgroup, right? H is a subgroup of G. right? And I just choose two elements from the group. In that case, so we have either the coset generated by G1 is the same thing as the coset generated by G2, or coset generated by G1 intersection with coset generated by G2 that's empty. Okay. So this is quite easy to prove. So it's just, I'm just going to look at this set. So I'm not going to, yeah. Let's just look at the intersection. G to H. So this is the proof part, right? So let's just define the intersection as X. So the first thing is if X is empty, then it is okay. Okay means, well, it is consistent with the claims of the theorem. So that's one case that the theorem says that should hold, right? If they are disjoint, they are already disjoint. There's nothing to prove in there. But if X is not empty, so that means there's an element K in X, but this is in the intersection, so therefore K is in the coset G1 and coset G2. K is in the coset G2. And because of the theorem that we have proved earlier, so we have shown that G1H is equal to K times H in that case. And similarly in here, the coset is equal to, again, K times H. So this then tells you that these two cosets then have to be equal, right? I mean, if these two cosets intersecting, then they have to be identical. They have to be the same set. All right? So basically, this is the end of the proof in here. I'll then go to the next step. So basically, it says this: if, G can be expressed as, so this is for left cosets. Sorry about this. It is possible that a left coset and a right coset might have some intersection which is not a coset, right? So, so this is true only for two left cosets, and similarly for two right cosets, right? So let me add this. So similarly for two right cosets. But there are situations. I'm going to give you some examples of that later when we go when we see this permutation group. There are situations where the left cosets and the right cosets are different from each other, so therefore they have some kind of non-trivial interactions. So this is the last thing in here for now. Basically, group can be expressed as a disjoint union of its left cosets, and then I'm going to add similarly right cosets. Okay, what I'm saying is this: suppose we have a group in here, group G, right? This is the group. H is a subgroup inside. And so basically I can then find other subgroups of the group which are basically left cosets. So there's some kind of an element in here, G1H, for example. There's some, sorry, it's not an element, it's a subset. There's a subset in here, which is G2H, and this is G3H, and so on. So I can basically divide this whole set into these left cosets. So basically every element of the group belongs to a left coset. And so therefore, all of these left cosets, their union somehow gives us the full group. Or I can do the same thing for the same group with the right coset. So let me try to draw the same picture again. So it's the same subgroup again, but this time we just do it for the right coset. So let's just say it like this. So suppose this is, sorry, HG1, and then we have, this is HG2, HG3, and so on. So it's basically a different structure in here. So let me try to show it like that. Okay. So in any case, this is then, well, this is basically the last of it. But there's this nice idea in here. So if G is a finite group, then I can notice this. Let me use a color in here. Each of these cosets have the same number of elements as the subgroup. So all of the cosets have the same number of elements. So let me try to show it like that. So I know that each GIH has the same number of elements as the subgroup. And so therefore, since the group itself is a union of all of these left cosets, so therefore the number of elements in the group is equal to number of cosets that a subgroup has multiplied with the number of elements in each coset, right? So therefore, from here, I can find a formula for the number of cosets of the subgroup H. Of the subgroup H, let me say it like this.
Hocam, these are the distinct left cosets, right? All the time we are talking about distinct. Disjoint means distinct here, right? Because
disjoint means empty intersection.
Yeah, in that case, they are distinct. Okay.
Yeah, G3H is, I mean, this coset is identical to only itself.
I see. Okay, thanks.
Yes. Disjoint union means the union of subsets which are all have empty intersection, right? So this disjoint essentially means empty intersection. So they don't intersect with each other. So in any case, we have a formula for the number of cosets, which is this. It's basically the ratio of the orders of these, order of the group and to the order of the subgroup. But since the number of cosets can only be an integer, this means that this is an integer. So as a result, this is the theorem. It's an important theorem, actually. It also contains some other theorems as well. Let's say it like this. The order of a subgroup divides the order of the group. So in this case, basically, H is a number that divides G. The order H basically divides order G. So that's the mathematician symbol actually for divisibility, right? So we say that 2 divides 6, for example. We use this symbol. In any case, there's no harm done if we just use words. Okay, so as a result, from here, for a given group, for a given finite group, we basically have a limited number of possibilities for the sizes of the subgroups. And so as a result, by using this, we can actually kind of search for subgroups in an easier way. So let me just say it like this. But of course, we will also see a little bit more powerful relationships later. Okay, but this is one of the things that we use a lot. So as a result, let's give it like this. Okay, so let me stop the recording.